Pre-calculus content lesson, we're going to talk about using E. Let's remind us that E is a special number from a previous lesson. It required a limit to define it, to discover it. E is defined as and equal to the limit as x approaches infinity of 1 plus 1 over n all to the n. We needed calculus to create this. And E has an approximation. It's irrational, so we can't write it down exactly. Like pi, its decimal approximation goes on and on and on and on. I'm going to write many decimal places in the expansion. I'm going to go farther than the book and typical resources because in the decimal expansion you can see that there is this, coincidentally, a repeated 1828. And in a resource that ends the decimal approximation there, it can give people the impression that 1828 is going to repeat indefinitely, but it does not. After that pattern repeats, there's a 4-6 here. E definitely doesn't have a repeating sequence. Like pi, it goes on and on and on. And if we are going to use E and have to approximate it in a math, of course, we want to get in the habit of doing so to the nearest thousandth place so that there's 3 decimal places of accuracy. 2.718, if you must approximate E, is typically sufficient. So using E, where do we do it? We had a context of using E in continuous growth or instantaneous growth. I'm going to write down an equation here that we used in a previous lesson. A is equal to P to the A is equal to P times E to the RT, where A stands for an amount, typically an amount of money, if we're talking about money growing in a bank account or an investment. P is the principal or the initial amount. E is the special number that we're using as a power base. And the exponent of that power is the product R and T. R for an interest rate or a rate of growth, and T for an amount of time, typically years in a banking context. So before we provide another example of using this equation in context, let's talk a little more generally about E as a power base. When we write the simple expression E to the x, then we're using, this is a power, this is an exponential expression because the exponent is the variable in this case, and E is the special number that we're reviewing and defining here. We know that the inverse of an exponential is a logarithm, and the logarithm, if it is going to be of the base of this special number E, is then called natural log. So if I write the natural log of x, this is a mathematical expression where the variable is x and the ln stands for the natural log. Natural log is a special term that we give to log base E. So ln x is exactly the same thing as log base E to the x. So when you see natural log being used in algebra and algebraic expressions, it has all of the properties and you treat it the same way as a logarithm. And I'll remind you that these are they have a parent function form, and the graphs of those I'm going to sketch as a review here quickly. An exponential function has this essential nature. If it is growing, that means the base is greater than 1, and E is greater than 1. It's approximately 2.718. So its graph, sketch of its graph, is going to be like this. It's an exponential function. And the natural log of x is just like all other logarithms, the inverse of the power base e. And we'll label this as an e to the x curve and this one as a natural log curve. They're reflections of each other over the perfectly oblique line y equals x. Okay, let's now take a look at an example. Let's work an example using this formula in context. And we're going to ask the question, what is the time? What is the time to double a 4% investment? So from this language, we're talking about money, the context of money, and money is going to grow because it's going to double. So we're going to borrow this equation, and good habit when we solve equations and we work on contextual problems is to begin with the equation that we're going to use without substituting any values and variables in yet. Start with the basic equation. And then we're going to analyze, well, if we're going to use this equation, what do we know and what are we asked to find out? We know that quite directly from the wording of the problem, immediately we have this 4%. 4% in this equation is the interest rate represented by R. So I'm going to say that R is equal to 4%. But immediately this 4% I'm going to convert to a decimal. If I'm going to use it in the equation, then I want to remind myself that the percent means dividing by 100. Literally, if we take the symbol and rearrange the O's in the line, that means the symbol stands for division by 100. And that, of course, is the justification of why 4% is the decimal 0.04. But there are many more variables in this equation. The problem is asking us to find time. So the variable time is our question. I'm going to represent what we're looking for here and write a question mark by it. Now, what else do I have in the wording of the problem? Nothing directly, but if I'm trying to find time and I have a value for R already, then the remaining variables that I must somehow find values for are A and P. The principal or the initial amount, and A, the amount after doubling. Well, they're not given as specific numbers in the problem, but if I think of the context, what it means to double is simply to have twice as much as what I started with. So I can invent a principal amount, a starting amount. I can make it up. And then A is simply going to be double that. So if I'm going to make up a value to work with for the principal, it might as well be 1. Very simplest number to work with. So doubling 1 would mean that my ending amount would be 2. I'm going to plug in the values that I know here into my equation. I'm going to do my work over here, and I will find that an amount of 2 will be equal to my starting principal of 1 times e to the interest rate of 0.04, and t is the variable that I'm trying to solve for and find. Checking this equation, if I start with a principal or initial amount of 1, I'm trying to find the amount of time that it will turn into 2, which is doubling. I'm going to solve this equation for t to find that amount of time. My first step is to divide both sides by 1 in order to get rid of it here. But I don't have to show that as a step, or I could ignore multiplication by 1. Might as well be thorough. If I want to undo this power base e so that I can get one step closer in getting t by itself, then I think, well, what is the inverse of the power base e? That's a log base e. And we talked about log base e being the natural log. So I'm going to take the natural log of both sides, which will undo the power base e because they're inverses. Here's showing the step of work. The natural log of 2 is a value, but I'm not going to approximate it yet. I'm going to keep it there. And on this side, the natural log of this expression will cancel out the power base e in this expression so that it leaves 0.04t. I'm going to continue my work up here where I have space. I'm trying to get t by itself, and I've got 0.04 multiplying t, so I am going to take the step of dividing both sides by 0.04, which will leave t by itself, and on the other side I get the natural log of 2 divided by 0.04. At this point I could go to a calculator to approximate it. I'll do that. And I'm evaluating the natural log of 2 divided by 0.04 on, doesn't require a complicated calculator. On this calculator I'm going to put in 2 and hit natural log. I get this decimal approximation, and if I divide that then by 0.04, I will get an approximation for t equal to 17.327 rounded to the nearest thousandth, which is a habit that we want to get in when we need to approximate. Notice that I could have approximated right here, but it is generally a good idea to save the final evaluation so that you get the most accuracy when you go to a calculator screen. I did the natural log of 2, which gave me all of the decimal places in the calculator screen before dividing by 0.04, which means that my final approximate answer is about as accurate as it can be. Is this reasonable? Remember, this is a context, so t and its answer should be given with the units in years. In the context of the problem, my final answer is that it takes 17 or a little more than 17 years to double any investment that I make, giving 4% interest rate or 4% increase on my investment per year. Is that a reasonable amount of time? Thinking about this, 4% growth per year, it's going to take quite a bit of time, 17 years, in order for my investment to double. I'm confident that this is the answer.